All right, we might get started then. I'd like to welcome you all to the Earth Systems and Climate Change Hub Science webinar. This webinar will be on understanding future extreme sea levels and the tools and information used to support coastal managers. Today's speaker is Dr. Julian O'Grady from the CSIRO. And Julian is a researcher within the Earth Systems and Climate Change Hub Project 2.10 on coastal hazards in a variable and changing climate. He has over a decade of experience using numerical models to simulate waves, hydrodynamics and sediment transport from coastal waters to the shoreline. He applies statistical analysis to investigate climate drivers and extreme events and to estimate the impact damaging storms have on coastlines in Australia and the Pacific and how this could change in the future. So just before we get started, a little bit of housekeeping. You will have noticed that you've all been put on mute and videos turned off. I do apologise for this. We have quite a large audience today and it's just to reduce feedback and also distractions for the speaker. So we might get started then. I'll hand over to Julian to begin his presentation. Thanks, Julian.
Thanks, Sonia. Can you hear me?
Yes, perfectly.
Yes, oh, that's perfect. All right. So the talk that I will be presenting is basically around the tools that are available on the web and a new tool that we're developing, which will hopefully be released very soon, to understand future sea level rise and on top of that, extreme sea level rise. And so from what I understand, there's a diverse audience that's participating in the webinar, so I'll try to give a broad overview starting, and the outline will be to talk about our place, the team's work within the Nest Hub, then give some background on the science of sea level rise and extreme sea levels, and then move on to live demonstrations of a new tool and also the available tools that are out there to investigate extreme water levels. So the Earth Systems Science Hub's priorities and responsibilities are to improve the understanding of past and current climate, improve the understanding of how the climate system may change in the future, building the utility of Earth System science and climate change information to ensure Australia's policy and management decisions are effectively informed by Earth System science and climate change science now and at the future. So, broad picture, the hub has separated into different climate challenges. So one around water resources, food, security, carbon cycle, changes of the coast, and extremes and disaster. The work that we are doing is obviously within the changes in coastal climate. And our work within that is to look at the impacts of coastal sea level. So this is a Venn diagram that people have probably seen before with hazard, risk, exposure and vulnerability. Often exposure and vulnerability are separated into a separate circle, but I've included them here together today just to say that to separate who's working on what. On one side, we have climate scientists like myself and people in the team at CSIRO and at unis looking at the hazards. And in the exposure vulnerability, we have the stakeholders, coastal engineers, planners, people involved in insurance, finance. We also have researchers who are looking at universities who are looking at exposure and vulnerability, and also consultants. And they working in government at all levels, in universities and in the private sector. So on the hazard side of things, what we're looking at is projections of how high sea levels will get, and from mean sea level to extreme sea level. On the exposure vulnerability side, the information that is available is on the assets are how high the assets and their value. And where we're looking at hazards at the open ocean, in estuaries and on beaches, and the exposed and vulnerable assets are ports, residential circular, just for example. So where the hazards and exposure overlap is the risk, and really what we're interested in is who and what are impacted. The impact of the social, economical and environmental impacts to the community. And through the Earth System Science Club Hub, they're bringing the two groups together so that we're focusing more on impacts through these webinars and online tools that are being made available. So to get started on, that's the sort of background overview of where our team sort of sits in the Earth System Science Hub, in the hazard side of things. If I now move on to the background science, start with global sea level rise. So this plot here that's shown is, you've got time on the horizontal and mean sea level that's recorded from, global mean sea level that's recorded from satellite altimeters. And we can see trend, there's a seasonal cycle and an increase, an increase over time of around about 3.3 millimeters per year. So there's an observed increase in sea level rise. Sea level rise is also being predicted through the use of global climate models. And so different institutions around the world have submitted their climate simulations to the IPCC, and it's been analysed, projections from the models, the 2100 compared to a baseline centred around 1995, vary the different emission futures. But for a low emission future where the RCP, the representative concentration pathway, how much greenhouse gas concentrations in the atmosphere are at a lower level because of mitigation methods to reduce climate change. By the end of the century, we're expecting at least for a low emission future, 0.28 meters to 28 centimeters. And at the higher end, when we see a sort of business as usual concentration pathway, we're seeing much higher sea level with a mean of about 0.74 meters up to almost a meter, 0.98. And the trajectory of these different emission scenarios, RCP 2.6, the lower one in blue here and in red, and the range are shown on this time series plot. So this is from the available model data, but there's also the collapse of the marine base sector of the Antarctic ice sheet, if initiated, would add no more than several tenths of a meter by 2100. So there's also, you've got to account for the sea ice melt, terrestrial sea ice melt, which could influence how high sea levels might get by the end of the century. So I would just like to point out that here is the radiative forcing that pathways from the different RCP scenarios. Apologies for the colours not matching up here. But the lowest one is this green line where the radiative forcing reaches a peak in the middle of the century and then decreases as we go off towards the end of the century. And what we notice in the ocean sea level rise, that it's continuing to increase over time, and there's not an instant response to sea level rise. So this is due to the long-term storage of heat in the oceans compared to the atmosphere. Will continue to influence the climate system after radiative forcing has been addressed. So this is just reinforcing the fact that we do need to act on reducing greenhouse gas concentrations in the atmosphere to, today to really reduce the impact of sea level rise going into the future. So there's the background global mean sea level rise, but sea level does also vary regionally, so different parts around Australia. So this is a figure of the sea level trends derived from satellites around the coastline, as well as the tide gauges. So the colours indicating a trend in millimetres per year, low average being around 3. We can see much higher values around northern Australia. And And obviously the length of the data sets that we're studying determine the confidence of the trends and the agreement between the tire gauges and the satellite altimeter. This is just really just pointing out that the sea level around Australia is variable, and the latest AR5 assessment report 5 does account for changes in sea level around Australia. And if anyone's used the Coast Adapt web tool, you'll see that the sea level projections provided for each individual council around Australia, and they'll change. The sea level rise projections will change from council to council. On the right, these showing spatial maps of the end of the century, centered on 2090, the different RCPs, the emission scenarios, what the sea level trends could look like by the end of the century, with varying spatial patterns. And this information is used in the Coast Adapt web tool. So moving from mean sea level to extreme sea level, here's a figure which highlights the 1 in 100 year event, storm tide level. Which has an extended probability of 0.1 or 1% chance of happening in a year. So it's the level indicated of an extreme event. So we can see that it's much higher on the extreme sea levels are much higher on the northern Australian coast, northwest shelf, where we have high astronomical tides, as well as tropical cyclones, which can generate huge storm surges, which create large extreme sea levels. Compared to the southern coast, although where the continental shelf and the bathymetry are wide, they can support large storm surge, which can increase extreme sea levels. And on the right is a plot of a figure from McGuinness et al. 2016, showing a map of Australia and a figure showing some of the different climate drivers influencing storm surge and extreme sea level. So we have monsoon winds in the north of Australia, tropical cyclones, which can generate huge winds which push a lot of water up against the coast, and also the inverse barometer effect. The low pressure sucks the water up vertically and increases the water level at the coast. Frontal systems that propagate below the subtropical ridge, the downward arm of the Hadley cell, and the seasonal changes in the subtropical ridge mean the frontal systems and east coast low systems.
Julian, you seem to have gone muted. Hang on a moment. There. Try again. Sorry, Julian. Try again.
Sorry about that. Yeah.
Yes, you're back. Good.
Back again. All right. So where did I leave you?
I think just finishing off the last, the change over to the next slide. So if you just start at the next slide. Thanks.
All right. Sure. So this figure here is showing the contributors to extreme water levels stacked up vertically. So we've shown mean sea level. Around mean sea level, we have changes in sea level, regional sea level, an example being ENSO, changing the water temperature and changing the seasonal height of water level. Around that, we have tides, so high tides can cause extreme water levels, and king tides in particular. If we have a storm event that occurs, we can get storm surge on top of a high tide, which would cause extreme water levels, and then obviously wind waves as they go in towards the coast, they break and pile water up against the coast and are able to run up and cause higher total water levels at the coast. So if we obviously what contributes to total water levels depends on where you're measuring it. So if you're in the open ocean, the figure looks very different to what's on the left here, but the figure would look different. It's measured by satellite altimeters, and you're really just measuring mean sea level. If you're inside a protected harbour, so here we have a boat and a wharf and a tide gauge, we're measuring both mean sea level and you're including storm tide. So we're including storm surge, but we have sort of breakwaters that protect the infrastructure within a harbour, which means that waves won't influence the water levels. On the open coasts, which are expected to influence wave, we have the combination of mean sea level, storm tide, and wave effects. We have the full brunt. So depending on where you are in the coastal zone, or exposed beach, or in a harbour, or in the open ocean, you'll get different contributors to extreme water level. So the different web tools that are out there that I'll get to further on through the talk provide information on the different contributors. So the CoastAdapt website and the original CSIRO web page that provided sea level rise information will give you information of mean sea level rise up to around here, and including seasonal changes. In the open ocean, the Canute 2.0 tool, which we'll talk about, and the new 3.0 tool gives you information about the water levels from storm tide within harbours, so we can estimate water levels up to this sort of level. The Canute tool also had a function to look at waves at the coast through a very simplified tool. We're planning to improve the Canute 3 tool to include a more involved process for accounting for the probability of waves to extreme water level, and this will give you information about the extreme water levels at the coast. So Canute 2.2 and 3.0 will give you information that will service sort of bathtub tub filling. Canute 3.0 with waves will give you information around wave effects of overtopping and erosion potentially. So here I've made a screen dump of the many different tools that exist to investigate extreme water levels and water levels around Australia. So up in the top left is one of the first tools which provided information on the altimeter trends and also the climate model data and background information on sea level rise. So recently CSIRO, we've developed a new web tool, and we've migrated a lot of that information into the sea level waves and extremes webpage. So we'll show that in a bit later. And one of the first tools investigating extreme water levels is the Canute tool, where you can, click on a map and investigate what the extreme water levels are around the coast. This mainly focuses on the AR4, so an earlier version of sea level rise projections. CoastAdapt here provides information on AR5 sea level rise projections, as well as providing extreme water level allowances. So we can talk about allowances a bit later. So these are some hazard tools identifying how high the water levels are going to get. There's the coastal risk website where we can plug in these hazard heights and we can look at inundation maps. And I'll also point out there's another hazard tool. Before I mention that, I should have mentioned there's another hazard tool, which is the Marine Explorer within the Climate Change in Australia tool, which gives you similar information to the CoastAdapt tool, along with other information including sea temperature changes, sea surface temperature changes, and ocean acidification. And there's so these are the tools that are out there, and a very new tool, which is I think has only been released at the end of last year, is out of the University of Western Australia, is another tool where you can investigate extreme water levels around Australia by clicking. So the tool that we'll present today is similar to this. And I'll sort of touch on all these web tools and platforms later on. So the new tool that we're presenting, Canute 3.0. So what it does, it builds on the Canute 2.0, which was developed by the university. Sorry, before I move on, I got to mention that there's been involvement from a whole lot of different groups to develop these web tools, and there's a lot of overlap with the information that's passed between there. So there's obviously our group in CSIRO, but the University of Tasmania developed a lot of the Canute tool, along with the information from the University of Western Australia, and obviously Griffith and the Spatial CRC have developed a whole lot of information. So moving on from Canute 2.0 to Canute 2.3, so one of the biggest upgrades is that we're now including AR5 latest projections of mean sea level. It's providing sort of a more interactive tool with modern web-based functions and a framework within the team to develop Canute 3.0 new science on wave effects and projected changes in storminess, which the science that we're developing within the group. So the Canute tools really tell you about extreme water level climates. So you've probably heard of the term, a 100-year storm event, which really is used to describe extreme water level climate. So a 1 in 100-year event. So what is it? It's an estimate of the probability of a storm event happening in any given year. So a 100-year event has a 1% chance, or a 1 in 100 chance on average of occurring in any given year. So it's used to describe the climate of extreme water level heights. So the Canute tools can provide a 1 in 100-year storm, as well as other 50-year storm height or a 10-year storm height, or other water level heights to investigate the impacts. Why do we do it? Well, it's used. Why do we use the 100-year storm? It's used to design the height of coastal structures. So if you're going to build a coastal structure for X years, you might want it to live to not be inundated by a storm for X years, but you'd probably want it to be safe to be a longer sort of X plus years. So maybe, for example, if you design a structure or you have planning offsets for 50 years, to look for the next 50 years, you might want to investigate the 1 in 100-year storm. And it's also to look at your current infrastructure and see how you might need to change that for adaptation. And how is it calculated we use statistics. So to give a bit more information about, or a better feel for the 100-year storm, maybe we can simple explanation of how we generate the 1 in 100 years. So if you have 100 years of data, for example, then the highest storm on record can be thought to be the 100-year storm. So over the 100-year period, the highest event is what you'd expect in 100 years. For the second highest storm event, you have 2 events that are equal or higher. So it's the 50 years. So it will happen twice, so every 50 years. For the third highest storm event, there are 3 events equal to a larger, so that's the 30-year event for a third. So on average, you'd expect it to happen 3 times, and so on. So as you look at all the events within your record, you can rank them and see what the extreme value climate looks like. Obviously, the question is, if we don't have 100 years of data, we only have 40 years of data, how do we determine what the 100-year storm event is? So let's go through the example of saying this is a 40-year time series. So we have time along the x-axis and the height of the water levels on the vertical axis. And we can see a few events like higher than normal sea levels that appear. I've circled them here. So we can see perhaps that's the highest event, and we have some higher events. So what we can do is take those events and reorder them highest to largest and associate them with an empirical ARI. So 49-year event. The top event that we had in the record is a 1 in 49-year event. The second highest is half that, third highest a third, on the 49 years, and so on. And I've plotted this on a log scale with the years on the horizontal and water level on the vertical. And we can already see there's sort of a trend in these extreme events that we've ranked. They're sort of indicating a pattern of how high water levels are for different return level periods. We can almost see a line passing through it or a curve. So we can extrapolate that from your ride, say, well, 100-year event is probably somewhere over a metre, maybe 1.1, or maybe even up to 1.2. But using the data, we can actually fit a regression of a probability distribution, a Gumbel or a Weibull distribution to the data, which on a log scale, this is a Gumbel distribution, which it's a model, it's a fit of a distribution, which sort of shows how the regression of a model interpretation of a probability of what return level heights would be for different return level annual recurrence interval years. So the regression is fitted to all the data. So you can see here it's fitting well to the events that happen below a 1 in 10-year event, so the lower events. And some of these higher events, for example, from this example fit, some of these higher events are sort of, the regression is overestimating some of these higher events. Now we've got to remember, in a 49-year of data, we're not guaranteed to actually get the 1 in 49-year event. There's only a 66% chance of that occurring. And the same with a 1 in 30-year event. So these events, perhaps could be better represented. A 1 in 49-year event could perhaps be better represented by the extreme value distribution here, a value of that comes off the regression line. And we can also use this regression line to, finally extrapolate out and interpret what a 1 in 100-year event is. And I guess there's many different models to fit, and based on the available length of data, you can include extra parameters and improve the estimates of the fit. So the Canute tool includes these sort of model regression lines to predict what the 1 in 100-year, what the 20-year from data, and what 1 in 10-year event is, a whole range of return periods. And it presents this information in an easy to use tool. So the data sets that the Canute tool uses, there's a tide gauge network around the world with variable different tide gauge lengths, ranging from 100 years at Port Denison to much shorter at different locations. So an example is the Gessler database of global tide gauge records, which you can use to look at extreme sea level. So there's a web page and we can see all the locations around the world. But there's also been some hindcast hydrodynamic simulations conducted. So one in particular is the Mike 21 hydrodynamic simulations, 61-year simulations, and which are used in the Canute tool. And this outputs at 7,000 locations around Australia, and that was run by the University of WA with a reference to Haig et al. I should say 2014, and there was 2 papers that the group wrote. One was on a hindcast based on a reanalysis, and the second one is a synthetic tropical cyclone simulations. So along with the Mach 21 simulations, they also have recently completed some schism simulations, which is another hydrodynamic model. So this is, here we're showing a grid of the hydrodynamic model. Within the group, we've, the CSIRO team and our bureau, our colleagues who's moved to the bureau, we have a ROM simulations of 31 years with a similar 7,000 points around Australia, which includes, so this is the reference here is the Kohlberg et al. 2019, and the nice thing about this data set is that it includes climate change simulations, so we can look at changes in storminess. So we've talked about the 1 in 100 year event as a description of the climate, but there's also, to look at extreme water levels, there's, out of the University of Tasmania, John Hunter has developed the allowances estimate to account for sea level rise. So what are the allowances? What they use? Allowances represent the vertical distance that an asset needs to be raised under rising sea levels, so the present likelihood of flooding does not increase. So the allowances really take into account the extreme value distribution and the sea level rise to make a best estimate of how much to include, how much to raise assets to protect them, or to coastal defences to protect the assets. So in general, when the uncertainty regarding sea level rise projections is small, as in the case of the near future, 2013, closer to the present day, the allowances are closer to the median or the sea level rise range. However, as uncertainties become large in the climate ensemble, as is the case for 2019, towards the end of the century, the allowances also increase and tend to lie between the medium and the 95th percentile, the upper limit of the ensemble simulations of sea level rise. So the allowances appear in the Coast Adapt tool, along with further information about what the allowances are, as well as in the Canute tool. And the Canute 2.0 tool also accounts for the uncertainty of allowances and the extreme value curve and the design risk calculations in determining the extreme water level heights. So closely linked to the one, the annual recurrence interval is the annual exceedance probability, which refers to the probability of a flood event occurring in any year. The probability is expressed as a percentage. So, for example, a large flood, which may be calculated to have a 1% chance of occurring in any 1 year, is described as a 1 AP. So 1 in 100 is 1 in 100 year event. So here I've just pulled this table out of offline. This is referring to rainfall AEPs and ARIs. We can see that 1% ARI corresponds to a 1 in 100 year event. A 1 in 50 year event corresponds to a 2%, so 2 in 100 annual exceedance probability. So the annual exceedance probability and annual recurrence interval are all based on it for occurring in any given year. So in one single year, so a year now or a year in the future, say 2015, what's the probability of that occurring? But if a coastal asset is built, then there's over the life of the period, there's multiple years, and the chance of exceeding increases. So I guess the Canute 2.2 tool includes this information for people who are designing coastal structures, and the plan is to include this information in the updated Canute 3.0 tool. So now I'll get on to the live demonstration. So I'll start here at the Sea Level Waves and Coastal Extremes webpage, CSIRO webpage, where we have details on our research in sea level, so the global sea level rise information on waves, coastal extremes, some work we're doing with wave energy converters, and of course got information on our site on our people that are working in the team. So you can go in there and have a look. But we're here to look at the Canute tool. So obviously tide gauges provide the most direct observational record of extreme sea level, and they are included in the Canute tool, but we also have model hindcast data. So the Canute tool, here we have links to the tool. So we have the CoastAdapt tool linked down here, but we've also got a link to the former Canute 2.0 tool. So to access the Canute tool, you need to go through training and access a username and password to use the tool. But we can log in and access the tool.
Hey Julian, you might need to share your desktop so we can see the tool.
Oh,
we're still on the presentation.
Apologies.
No
I knew this would happen. Okay. So can you see the web page now?
Yes, perfect, thanks.
So I'll just quickly go over this again. This is our sea level waves and coastal extreme web page with all the information on sea level waves, extremes, and wave energy converters, and our people. You can scroll through there and have a look. So here is a link to the tools. So, and here we can click on the Canute tool. And we can scroll in to different locations and click on a point to find extreme water level information. Click next. So we can select different greenhouse gas emission scenarios for the different RCP 4 AR4 and AR5 starting year and end years. We can look at GV and gumball fits, and so this is the original Canute, and it generates these exceedance probability curves which show the probability of exceeding a certain water level height, and the blue line being current climate and the future being the allowance in red. So new version of Canute. So this is the new tool that we're developing in the Earth System and Climate Change Hub. Looks like this. So again, there is no user sort of permission. Anyone can access this website when it's made live, which is hopefully by the end of the week. This will be live and available to everyone. So on the left, we have a whole lot of functions to plot, and on the right, a map of Australia to select. So for example, if we're using the tool to look at generating a report for a coastal hazard assessment for a local government, for example, let's have a look at Williamstown. We can switch between a tide gauge, so the tide gauge information there. We have a look at the local model grid point. A disclaimer comes up, which we can approve to use the data. So what this does is it switches from the map view to a summary tab, and we can see the plot here and table of data. But before we get into this, we probably should have a look at what the other tools are that are out there before there's the Canute tool we're using. So the sea level rise information that's used in Canute is the same that's used in the CoastAdapt tool. And Canute will provide a link automatically to the local coastal council. So we clicked on Williamstown, and a point near Williamstown and the local council is the Hobson Bay. So if you click somewhere on the New South Wales coast, you'll get the local council there as well. You can click on that and that will open up the web page for the Coastal Adapt tool. So hopefully most people are familiar with this. This is Coastal Adapt tool, which shows the AR5 projections, and you can enter in different councils here. It provides all the sort of hazard information in a plot form and tabulated. So we could easily just grab this information, copy it, and if we were to, for example, start a report on the Williamstown Coastal Hazard Assessment, something I prepared earlier. We have sections on hazards, exposure and risk, just to follow the introduction of the talk. We can paste the table and here we have information about sea level rise. So, for example, we might be interested in, sea level rise 2013, what's under a high emission scenario. So we can put that in bold as a starting point to look at the Canute tool. Now, I'm just giving you a very basic example of how to start a report, but if we go back to the Coast Adapt website, there's a whole lot of very, very useful guidance on how to generate these sort of reports and provide information. So there's guidance on risk assessment, local risk, first pass. So I'm really just showing you how to get hazard information into a report. I'm not showing you how to develop the report, but we can see here's a similar, how to conduct a climate change risk assessment at a glance. It gives you all this information on how to do a really good climate change assessment. Talking about risk hazards. So there's a whole lot more information than what I'm able to provide in this webinar on the hazards and the risk and the impacts. So recommend spending some time on this website if you're interested. So we have the sea level rise information, and we also have allowance information. So we can pop that information into a report as well. Just copy and paste, and it looks fantastic.
Sorry, Julian, you've just flicked back to, we've lost your screen share.
Okay. Sorry about that. Let's see if I can get it back. Are we back?
I think so, it's coming. Yep, there we are, back onto the website.
Okay.
Fab. Thank you.
No worries. So there's the start of the sort of hazard information that we can get for an assessment report, or not assessment report, a hazard report through Coast Adapt, but through Canute we can also link to the Climate Change in Australia web platform. Now this has a whole lot of information about terrestrial and marine climate change. And a whole lot there's 14 tools to investigate the data, and one of the tools is the Coast and Marine Explorer. So it's worth putting a link into there. We click to a point near Williamstown, we can see all this information on projections, and then also the different experiments or the RCPs and the allowances, so we can extract that. So there's a whole lot of information there. So now we can see what the data is behind, the sea level rise information is behind. We can now go and choose a future. So let's choose to plot a very high greenhouse gas scenario, perhaps to the upper, and with a baseline of 2050 and going out to 2030. So we can see, here's an indication of what's plotted. So we have the tide gauge, which is located very close to Williamstown, is this green line. the ROM CSIRO hindcast extreme water level distributions. The black we have in this sort of cyan, the original Canute, Mike 21 extreme water levels. And then we have curves or lines for the Mike 21 with sea level rise and with allowance color coded here. All this information is contained in this lower sort of table. So in the report, we've dumped the data, we can see for 2013, the highest scenario, we're seeing, 13 or so, 12 to 13, and we're seeing sort of similar sort of sea level rise allowance here, and then for the upper percentile, very high scenario, we're seeing 70%. And so when you look at the present day hindcasts and tide gauge observations, they're the annual recurrence interval values for the 1 year, 10 year, 20, and then we've just added on sea level rise. So we can easily download this information, and it comes in the form of downloads into a CSV file, which you probably won't see this information come up as I click it, but an Excel spreadsheet has popped up and I'm just selecting all the data from that, and we can paste it into a Word document. And it's not great, but we can reformat it in Excel, and we're well on our way to populating hazard information into a assessment report. So we can also copy the image and stick that in the document. We can change the plot of it. We can switch from ARI to now looking at an exceedance probabilities, and we can look at custom sort of plotting. So where if we click to customs, we can take off the log scale, or we can change the vertical scale, so we can investigate the sort of still water level information a bit more. So with these heights, we can then move on to looking at the coastal risk in Australia and selecting Melbourne, picking off, what's a 1 in 100 year event, 1.39. Sorry, manual. We'll say 1.4, and we can start to look at, what's a 2013 high emission scenario 1 in 100 year event might look like, and the sort of exposure areas. Okay, so I'm aware of time, Sonia. If we, I have extra slides to go back to, but I can stop there if you like.
We've probably got 1 or 2 minutes if you just want to sort of wrap up and touch on 1 or 2 more things. Okay,
well, I mean, I guess that's just an example that I've provided of the tool and how we can access the information and where it sits in the larger examples of the tools, of the other tools that are available. So the plan is, are we back? Sonia, can you tell me if we're back with the slides?
Yes, we're back to your slides, yeah.
We should see on the left here, we have ensemble statistics of the 1 in 20 year event. So the middle being the ensemble average, the top being the ensemble max. And this is the change, these plots are showing the change in the extreme storm tide. Not storm tide, sorry, the storm surge. So how storm surge heights will change. So the mean ensemble isn't showing, on the order of centimetre changes, these very light blues and reds. On the upper limits of the ensembles, we are seeing large changes in the Gulf Carpentaria and perhaps in southeastern Australia. And these sort of changes have been linked, well, work that's going to be published pretty soon with Kohlberg et al. linking these sort of changes to changes in the subtropical ridge and the monsoon winds that are in the climate models. So we're also looking at including waves. So we have, for each coastal point around Australia, we have the time series of storm tide. We also have a wave hindcast that tells you wave height, and we can estimate wave setup from the wave height. So we can add those two time series together, just stacking them on top of each other, generate the total water level, and that will give us extreme events. So on the left, we have the storm tide heights, the extreme water levels that come out of Canute for a 1 in 100 year event. This is the wave setup, the contribution of waves that could happen relative to mean sea level. So obviously the large wave climate across the southern margins of Australia, the large swell in the Southern Ocean generates the high wave setup along the southern coast. When we combine them together, we can see this sort of pattern of where the total water level heights are the largest, the locations exposed to the waves. And we hope to include that in Canute, where we can zoom into locations. There's a tide gauge. We have a list of beaches from the Australian Beach Safety database. And we can click on a beach. And we can see the plot up the top shows the annual return intervals for setup, and then this is for the storm tide. This is the original Canute 0.2, and this is when you include waves. You can see that there's a much larger estimate of extreme water levels. But wave setup is very dependent on local characteristics, in particular the beach slope. So when we don't consider beach slope, this is what it is. But we can, if, for example, location has a steep beach face, we can modify that to investigate how high the total water levels are for that location. And I guess the last, another addition to the Canute tool that we're investigating is that a lot of these tools are to look at bathtub inundation. We want to use the information within Canute to output time series for dynamic simulations of inundation. So obviously as the tide rises and falls and you have a storm surge, we want to be able to simulate that to look at the duration of inundation at certain locations. So part of the NEST Hub, another sort of project we're involved in is looking at the CFAST model, the city scale flood simulation tool, to look at dynamic inundation for local infrastructure. Okay, so I think I'll conclude there about the Canute tool and future versions, and hand back to Sonia for any questions.
Fabulous, thanks Julian. Thanks for a really quick overview of the Canute tool. Obviously it's got a lot to offer, so do go into those various websites and have a look. I've posted a few of them down there. So we do have a few questions. There's time for 5 or 6 or 7 minutes. So if you do have questions, write them into the chat box, the Zoom chat box, and I'll get to them. But to start off, our first question is around, is there any guidance on which plot type is the best suited for a risk assessment, for example, at a local government level?
I mean, there's no harm in including both types. Yeah. So having exceedance probability curves, or to have the ARI return curves. Certainly, if you have a preference, you can stick it in the report, and then in the appendices put an alternative plot. Should be relatively straightforward to switch between the two and screen capture and copy the images and dump them in.
Julian, is there any sort of guidance or background material on Canute that talks about, the difference between the plots and when you can use one plot and in which way? Is there that sort of information?
Beyond this webinar, there's not a sort of a walkthrough document which will probably perhaps be useful that we could develop to show how to step through all the processes. So yeah, that's something that we can definitely develop. There is a lot of information around the tool in general, the science and the engineering behind the tool in the Canute 2.0 website at the moment, which still exists, which is still online. So yeah, we'll try and make more information available as we continue to develop the Canute webpage.
Okay, and we also have another question that asks, what is the value in having so many models or so many websites for coastal examples? You know, you talked that there was Coast Adapt, there's Climate Change in Australia, Canute. Do they complement each other or compete, or do they form a sort of background of evidence that's useful?
I think they all add to the information that's available, and you know, the different web pages are definitely the developers of the different web pages are definitely in discussions to how we can make the integration across the different sites more effective. I mean, I've shown that you can, you know, through the Canute tool connect, but there's probably we'll be investigating improved ways of making, you know, the integration of the data. I mean, there's a lot of data that's being shared and presented in all the different websites. So it's just about, you know, making sure they all link up and are aware of each other, I guess, for the users.
All right, we have another question that asks, how do the tools calculate extreme water levels within bays or estuaries, for example, Sydney Harbour, where maximum water levels are known to be significantly lower than on the open ocean? What's the best tool for this?
Yeah, so the Canute tool is based on the storm tide information. So what you'd get out of a tide gauge in an estuary, which are typically located in estuary. So the Canute tool currently has that information. Our plan is that future Canute tools will look at open ocean, where there are wave effects, you know, beaches, and you know, rocky coastline. Well, perhaps not rocky coastlines, but fringing reef coastlines to investigate what the extreme water levels are with the influence of waves. But at the moment, the Canute tool is you know, designed for the sort of still water level information that is mainly observed in estuaries and harbours.
And you said that Canute, the new 3.0, is going to be up and running by the end of the week. Is that correct?
That's correct. Yes.
Excellent. Just in time.
Yeah.
So
well, I didn't want to get it running today just in case during the live demonstration it crashed.
Okay.
From all the thousands of people who want to use it.
Okay, we do have one more question. I'm not sure if we've got time for this, but the question was around, are you able to show us how to develop a super high tide inundation polyline of Southern Australia?
Of the whole of South Australia?
I guess. Or is it you need something more specific?
No, I'm not sure. I mean, if that's a feature that, you know, it would be useful to a lot of the users out there, I'm sure we could develop a functionality within the tool. But at the moment, that wouldn't be a straightforward process to go through the Canute tool. Okay.
No worries, that's fine. Well, that's all the questions we've got for now, and we're bang on time, so we might finish up there. Just wanted to say thank you very much, Julian, for your webinar and the live presentation. I think you've shown that there's heaps of great tools out there that people just need to dive in and see which one fits their needs best. So just a little plug for our next webinar. So our next webinar is going to be on the 16th of April and is given by Dr. Pandora Hope from the Bureau of Meteorology. And she's going to be talking about extreme events and the role that climate change plays in these, with particular focus on Australia's recent hot summers. So stay tuned for that. We'll send around a reminder as usual when that webinar gets close to the date. So once again, thank you very much to Julian, and thank you also for everyone for attending today's webinar. Julian, there's that last slide there that has the Hub's detailed contact numbers.
Apologies.
So if anyone wants to get in contact with us or with Julian, has questions about the webinar or the websites or how they connect, do feel free to write us an email and I can pass on any of your questions to Julian or any of his colleagues. But in the meantime, thanks again, and look out for next month's webinar. Thanks a lot.
Thank you.